So welcome everyone. I'm really excited to be here and have the opportunity to give you an overview about Eclipse GLSP. And GLSP is short for Graphical Language Server Platform. This talk is a little bit different from the context than the ones before. So before I go directly into the topic, maybe just to set the stage a little bit. Eclipse GLSP is not directly about building IDEs and bringing them into the cloud, but it's really about building diagram editors within those IDEs that you can then deploy in the cloud, whether it's Eclipse Thea or Eclipse or VS Code, whether it runs in Eclipse J or in other cloud-based environments. So it's really about building diagram editors within such editors. And the idea here is that we want to build these in a modern way. With that, I mean basically that we want to achieve an HTML5 based front end, like we also see in, for instance, Thea or VS Code, obviously. And with that, of course, there comes many benefits. As I already said, you can consume these editors in the browser or in VS Code and Thea. However, it also has some consequences architecturally, and we all know these consequences, which also have lots of benefits, of course, from textual programming programming languages like Java support in VS Code or TypeScript support, because they are not directly implemented anymore in the editor itself, but they are implemented in a backend, the language servers, which basically encapsulate the whole language smarts. And with Eclipse GLSP, we kind of want to do the same thing, but for enabling cool diagram editors, as we can see, for instance, here. So we have a front end that is a diagram editor. And at the same time, this diagram editor, which is really just focusing on the front end, is supported by a backend service that implements the smarts of a diagram language or a graphical language. So with that, basically applying the same architectural pattern of the LSP to graphical modeling, that's the main goal of the project, which is open source, hosted in the Eclipse Foundation. So you can go right onto GitHub and check out the sources and try our examples. And with that architectural pattern, basically we can achieve the same benefits that LSP provides for textual languages, but for diagrams, which is of course enabling the development of browser-based diagram clients, having really a front end that is focused on rendering and user interaction, and as I said before, encapsulating the language smarts entirely on the server, and of course having a protocol in between. So therefore, the project provides four main components, I would say. It provides a framework, which is Java-based, for the server to build specific diagram servers. So you can use that framework to build, for instance, a diagram server for UML class diagrams, for sequence diagrams, business process modeling languages, or whatever graphical language you would like to achieve. The second part it provides is the protocol definition, which concerns things like the language configuration, notifications about executions of operations and stuff like that. And then similar to the server, but on the client part, it provides also a framework then on the client to really build the diagram editing, rendering, visual feedback part that is then running on the client. Last but definitely not least, it provides also platform integration. So you can take editors that you've built based on these three components and then quite easily integrate them in different tool platforms like Thea. I already mentioned Thea and VS Code, but even also Eclipse, the traditional rich client Eclipse platform, or even standalone in a plain web application, of course. It's worth noting that the project heavily uses other open source technologies as well. So we build actually the server, the Java-based server is built on LSP4J, which is an excellent framework to build JSON RPC servers, which happens to be also used for LSP4J when you build other language servers for textual languages. So we basically use the same underpinning there. And on the client side, we use Eclipse Sprody, which is an SVG-based rendering framework, which is very nice, as it allows you to render interactive SVG diagrams on the client. And we also reuse parts of their client-server protocol for model transfer. So that's just a rough picture. What I really want to also focus on a little bit today is to talk about the specific challenges that we faced, or that anyone would face, I guess, when trying to adopt the language server architectural pattern and apply it to graphical languages or diagram editors. Because obviously the goals are the same, the benefits are the same, but what really is specific to diagrams. And what we learned, just pick the three most important ones, at least from my point of view, we really learned that that there are three key characteristics that also heavily influence the architecture, and that I would like to highlight a little bit here. So first of all, rendering flexibility. So when you think about diagram editors and different diagram languages, I already mentioned, for instance, class diagrams like we see here, or some workflow diagrams, function block diagrams, and so on. They all look pretty different from each other, right? And this is something that is very much different from text editing, right? Because text always is just text. It doesn't matter whether you're implementing a Java program or a TypeScript module. In the end, you're just writing text. So it's the language server doesn't really need to care about any part of that different looks of different diagrams, because it's always just text. So that has a big influence. The second one, which is I think also pretty important, is the what we sometimes call the impedance mismatch between the diagram and what is actually stored in a text file that is the serialization of this diagram, or can also be a database. So with text files, basically what you see in the editor is directly what is stored in the text file, right? So the source file is directly shown, and there is no difference between what you see in the editor and what is stored. For diagrams, it's pretty different, because the content from whatever serialization format that you need or that you use is sort of interpreted and then transformed into a diagram that is then rendered in the client. And that, of course, has a big impact as well. And last but not least, generic editing. It's also a very key aspect that is different. So diagram languages typically constrain the way how you're allowed to edit a certain diagram. So whether you can resize certain nodes, which nodes can be connected, where you can add child nodes, and so on. So a diagram language puts constraints on that and defines rules, and those are essentially the diagram language rules that a diagram editor needs to implement. And that's, of course, also extremely different from text editing, because it doesn't matter which language you're using, text editing always works exactly the same way. You're allowed to remove or add characters, essentially. And for diagrams, that's completely different, as I said before. And this really has a pretty big impact on the way how the GLSP protocol and also the separation of concerns between client and server is architected. And I will show you in the next couple of slides where it has quite an impact. So let's look at the protocol a little bit, and also then I head over to some demos and look into the source code to get a better feeling about that project. So first of all, pretty similar to when you start editing code, when you open an editor, also GLSP does it very similarly for diagrams. The client would send an initialization request basically to a language server, which would then initialize, start up, take the URI, and start doing its job. However, as I mentioned before, there is this difference between what is stored in a model and what the user would actually should see in the diagram editor. The impedance mismatch that I was talking about before, and then there is this high flexibility that we need in rendering. So what a graphical language server would do now, instead of just loading the text and start parsing it, it would load an arbitrary model source, whatever it is, a database, a text file, some XML or whatever, and would translate that into a so-called abstract graph model, which is basically an abstract description of what is going to be rendered on the server, on the client. So this description is, as you would imagine, it's basically a couple of nodes with types, maybe some attributes. Nodes can have children and so on, and then there will be edges between them. But it doesn't specify anything about which rendering technology and so on is involved and so on. So this graph description, which is a description of the diagram that is to be rendered, will then be sent to the client, and the client would then go through this abstract graph description and would translate it into SVG. As I mentioned here before, we are using here EclipseSource, which is a great technology that can do that really, really well. Basically, what it does, it takes each of these nodes, looks up the type, and then from a registry get the specific renderer or view, and then would translate that into SVG. So let's have a look at how that looks like in a real application. So I will just move the browser here. In this browser, I have a running Eclipse Thea instance, and there is an example 1.wf file for which we registered a diagram editor that we've built with GLSP. So when I double click it, you see that we have here this nice diagram editor. And what it essentially just did is read in the model source, translated it into this graph model, and then started rendering it. And then we can do all the typical stuff that we want to do, like zooming in, zooming out, and so forth. The rendering part, just to give you a little bit of a short idea of how this works like, basically is, as I mentioned before, so each of those node types, they are declared as a string, like this one here. They are mapped to a specific SVG view, and this SVG view just takes any instance of these nodes and then would basically translate that into SVG. And the code that we see here, basically this registration of model elements and this translation to views, that's exactly what EclipseSource provides. So with that, you can really easily define how each of those node types and edges should look like in SVG. We can even, of course, very easily modify it. So when we just to give you an idea, copy in some random SVG code here in addition, then go back to the browser and reload this diagram. Now we see that instead of that, in addition to what we've rendered before, we also now render this nice firework here. So with that, we have sort of covered the rendering part by this first issue, the rendering flexibility, by having this abstract graph model and then a very, very flexible rendering framework on the client. So what about editing? As I mentioned before, editing in text is always very much straightforward. For diagrams, it's a little bit different, since only the server has the knowledge of where it originally loaded the model from and how it translated it into the graph. It also is responsible for doing the actual modifications, right? Because only the server has all this information. So how we achieve that is by introducing a couple of different actions. One example is the tool palette action, but there are also many more, which is a way that the server basically can communicate which operations and actions a user can actually apply in which contexts. And it specifies the type of operation it is that the user can apply, some additional UI information like labels and so on. And which action the client needs to trigger when this action is actually being to be executed. So whenever you have, for instance, a couple of tool palette actions, they will be shown in the client. So that's the easy part. What happens if a user starts actually using those actions, then the client would just unpack the shipped action, fill it up with parameters like location and so on, and would then send it back to the server, which then obtains the registered handler for it, which typically then modifies the original model source. So that's exactly the same model source that we loaded in the first step. So it directly modifies this model source and then regenerates this graph model again and sends it to the client. So this step is more or less the same as we had in the first step, but now instead of just plainly loading it, we modify it first and then regenerate. So let's have a look at how that looks like. So when we now have here this nice palette, when we start now creating an automated task, basically the client was not aware what is actually how the diagram actually changed. It just knew that there is an automated task palette item, which is a create node item. And then by executing it, we just sent a message to the server, execute on this location, this action. And then the server did basically the rest. Of course, this works the same way also for edges and stuff like that. The same is also true, of course, for other editing capabilities. So whether you can connect, which elements you can connect or which labels you can change, the actual modification is always done on the server with exactly the same round trip that we have seen here. Of course, there is one additional catch to it. Basically, we want to avoid lots of round trips when we have direct user interaction. And this would happen, for instance, if you look at the demo again, and we have special cases like we are only allowed to connect nodes with certain edge types. So here we have a special weighted edge type, which we are allowed to connect from these decision nodes to any other node, but we are not allowed to start them from another node type. So you see here now this forbidden mouse pointer. So we would like to avoid having round trips when we hover over any element to ask the server, is it allowed here or is it not allowed here? And to address this problem, so GLSP provides a concept that we call type hints. So basically these type hints specify all the different type of operations that you can apply in the context of an element type. And an element type is corresponding to these node types that we've talked about before. So basically with these element types, node types, you can specify whether, for instance, an element can be deleted, whether it can be resized, whether it can contain other elements and stuff like that. And this is then sent to the client, which can then interpret those generic descriptions and already, for instance, decline creating an edge, as I've shown before. We can also have a brief look maybe on the server, how the server implementation, which provides these element types, look like. So just to look at the code real quick, maybe make it a little bit larger here. So in this diagram configuration, we specify the element types and node hints for this particular workflow example. And we specify, for instance, here that these weighted edges that we've seen before can only be connected from decision nodes to any other nodes. So when I now change that, that also from manual tasks, we can create those source element types, so those edges. Then we just reload this editor real quick, try this again. And now we hopefully can start to create edges from here as well. Right. That's very, very rough overview of basically how we overcame these differences between textual and graphical editing and applying the same architectural pattern of the language server to diagrams. Of course, there is much, much more to it, and Eclipse GLSP also provides lots of other capabilities, which I can't go into detail in 20 minutes. But what I would also like to point out real quick in the end is that it provides, as I mentioned before, different tool platform integrations so that you can run it in Thea and VS Code, for instance, and even the rich client platform of Eclipse, which I won't show here today since this is about cloud tools for now. But I really briefly show you how the same language server or diagram server that we just saw also can be opened in VS Code. So now instead of Thea, I have a standalone desktop application, VS Code here, and I can essentially start the same diagram editor, and it talks to exactly the same server that we've seen before. And I can hopefully prove that to you by showing you that here we can now also start edges from the manual tasks, which we couldn't do before our change that we did in the source code a few minutes ago. Besides just these plain integrations, we have also a couple of other integrations that go beyond just, for instance, being able to open, I don't know, stuff like undo, redo, and so on is of course integrated, but it goes even way beyond that. So for instance, in Thea, there is also the problem view integration that, for instance, you show all the validation markers that the server sent. We propagate that to the platform so that you also get these little nice markers here and that you can directly jump to the element and so on and so forth. There is much, much more, of course, but it's best to check out the example yourself and explore the different types of integrations that are available. Right. With that being quite close to the end, I think from the time, since I really want to make sure that we have enough time for questions. Just a few cool stuff that I want to highlight that has been happening in the GLSP community. So there is a couple of nice editors that have been built on top of GLSP, from commercial ones and open source ones, like UML, eCore, and the function block diagrams, and much more. And of course, there's also nice other projects where people extend GLSP to achieve certain functionalities. One example that I typically like to highlight a lot is an extension of the debug adapter protocol, so that you can step through diagrams same way as you would be able to step through code with the debug adapter protocol. So it's basically the same idea as LSP to GLSP, but now applied to debug adapter protocol, which was much easier, but also had its own challenges, which I can't go into too much detail here, but it's a nice project as well. Right, with that, I think on the last slide. In conclusion, I think won't go too much into detail to save some time, but I think this encapsulation and separation of concerns that this language server-based architecture provides is not only super flexible in terms of that it puts a lot of pressure from the front end, and you can more easily build HTML5 based clients, but it also is a very interesting way of improving the flexibility in deployment, the flexibility of whether you're running on one local machine or in the cloud. And last but not least, it also keeps, I think, the responsibilities of the different components pretty clear and straightforward, I think. I also want to highlight Eclipse project again, which is a pretty cool open source project in Eclipse, because it's, you've seen the rendering, it's providing very, very nice and flexible way of specifying these SVG renderings with animation support and really cool features. And last but not least, what I want to mention is that our experience with different projects where we've seen GLSP being applied is that it unlocks a very high reuse on the server. And this is not too promising, because I think LSP was designed with the same idea to reuse lots of language support, like indexes, abstract syntax tree parsing, and stuff like that. We see a very, very similar effect here with GLSP as well. So you can quite easily migrate existing diagram implementations by cutting by factoring out the business logic from that, and then hook it up with GLSP to basically migrate your non-web-based diagrams onto GLSP, and with that web-based diagrams, which is cool. And last but not least, it's, I think, really crucially important, and I agree with the presentation that we've seen before, that the choice of editor and IDE platform is really key. And in that sense, I think it's pretty cool to be able to build diagram editors that are not limited to one IDE platform like Eclipse, for instance, but can be actually quite easily deployed in multiple different IDE platforms and deployment scenarios. Right, with that, thank you very much for your attention, and I'm really looking forward to your questions.
And so thanks, Philip. That was really interesting. There's a number of questions in the chat. The first and possibly most important is, what type of turtle is it?
Oh, it's a, oh no, I'm not sure if I know the exact English term. So it's a Mississippi turtle. I don't exactly know the Latin name either. I can just say that the German one, it's Höckerschildkröte. So it's about 15 centimeters in size and 22 years old.
Okay. That was going to be my next question. As the parent of a boy who loved turtles, are you aware how long turtles live? So,
yeah.
The longer living pets. Okay. So the first question in the chat was about collaborative editing. Do you support more than one person working on the diagram at a time?
Yeah, very good question. So I think currently the GLSP architecture in that sense is very similar to the language server architecture. So it's the main use case is that for one workspace and one user, there is one instance of the GLSP server. So it has no collaborative features built in. However, that doesn't mean that it could not be attached to it. And I think that's again a pretty nice architecture, that instead of building all different types of features into the server, rather having it as a separate feature and extensible in that sense makes architecturally, I think, more sense. So what we haven't worked on that in detail yet at all. So I'm not aware that anyone in the community has done it. But I think what would be a cool approach would be to be able to connect multiple GLSP instances so that they get synchronized in their current diagram state, rather than having multiple people connecting to the same instance, because this is then very similar, I think, to other approaches for textual collaborative editing like telemetry and stuff like that, which also doesn't try to break break this architecture, but having multiple, also for instance, Eclipse J instances in different containers, but they can communicate with each other by synchronizing their state.
Okay. There was also a comment about, you mentioned text is always just text. You should tell that to people who worked with Unicode or RTL.
Yeah, of course, I always overly simplified it.
That's fine. I had a question. Do you have models or have cases where people are editing both text and diagram at the same time? You know, sometimes you do want the source, but it's easier to conceptualize and make larger changes when you can see the, the visualization of it.
Mm-hmm. Right. So we have those use cases quite often, actually. So I think there are two typical scenarios. The one scenario is where you have for some parts of your backend model a graphical representation, and for other non-overlapping parts textual representation, and they can reference each other, the concepts in the textual model and the concepts in the graphical model, but they are not editing exactly the same concept. So this is super straightforward to implement. Basically, you what I've shown here. So basically, this arbitrary model source can be, I don't know, an xtext-based DSL, textual DSL, and then we have a DSL that is, or a part of this meta model or this abstract syntax tree is modified only with graphical terms, and the other one is modified with textual editors, but they can reference each other. It gets a little bit more difficult, of course, when you have overlapping parts where you really can edit alternatively either graphically or textually, because then you run into this problem that you need to automatically generate layouts and so on the fly, which is possible with another Eclipse project called Eclipse Layout Kernel. However, it adds additional complexity to the whole scenario. It's possible, but you need to come up with strategies to mitigate those extra challenges.
There was a question about transaction size and scalability. Would compression over the nodes take more compute than it saves in bandwidth? And I guess related to that, how have you tried scaling?
Right. So I think there is 2 points or two parts where performance really makes a key impact. The first one is sort of the model loading on the back end. So that's of course something where GLSP doesn't really impact the whole performance. So whether the model is large or not, this is something you need to take care of in your particular GLSP integration, how you can load models in general efficiently. The other part is then on the client side, the rendering, which might be expensive. So I think in our opinion, with Eclipse Prod as a rendering engine or as a rendering framework, you can mitigate the performance hit for very, very large diagrams pretty nicely. And you can do that basically with 2 things. First of all, you can only render what's really visible in the browser. So you only render parts that are visible, but not something that is outside of the viewport. And the second approach, when you then zoom out, for instance, and you would show all of them, you can decrease the level of detail. So you just avoid rendering certain parts of the diagram to, again, keep the rendering as efficient as possible. And if you apply these 2 strategies, I think well enough, then the performance is outstandingly good in my opinion, or in my experience, especially when you compare it to rich client application performance that we've seen in other, for instance, GMF3 based technologies, where large diagrams really can pose challenges to performance. We didn't see those yet on the very, very fast SVG rendering speed and with those two approaches that we've talked before. And to your comment regarding, or to comment regarding compression of those G models that we've sent back and forth, so far we didn't encounter use cases where I would say this would make sense. Maybe there are use cases, but I don't know, transferring 200 kilobytes of JSON is already quite a lot of data that you're transferring, but it would just still go within milliseconds. So I don't think it makes sense, but in some cases, maybe it does.
Okay, and one last question from the chat. You mentioned VS Code and Theia. Do you have a client on IntelliJ?
No, so we don't have looked into that yet, but it's obviously would be great to have an integration there as well. We would be very, very welcoming to any of those contributions that add more clients and client integrations.
Okay, and sorry, one more question just appeared. Can you clarify maturity? Are there shipping products on this? Where are you at in the life cycle?
So yeah, there are products that are being shipped already on GLSP. I mean, it's not like as mature as, for instance, I don't know, GMF or EMF, which has been there for decades, or for at least 1 decade. But it's still already, I think, mature enough for several use cases to be also used on production level.